Hi everyone, welcome back to this week's ZX seminar. Today we have Razin Shaikh back, who have done a lot of interesting work on the completeness and continuous variable quantum computing. And today he's going to tell us about a joint work with Bodhi and Harney on ZX calculus is complete for finite dimensional Hilbert spaces. And the floor is yours.
Thank you, Sarah. So I just want to give a disclaimer that my neighbors have decided that today is the best day to do some construction. So if there's a lot of noise and you can't hear me, let me know and I'll try to repeat. Okay, so this is about the completeness for finite dimensional Hilbert spaces, and hopefully this is like the last main completeness result that's left for ZX. So I'm very excited to present about this. So first of all, what is completeness? Um, just to recap, if you have two diagrams, D1 and D2, in your calculus, and they correspond to the same linear map, then we should be able to prove that D1 is equal to D2 using the rules of the calculus. And if we can always do that, then that property is called completeness. Now, I've given a very I'm going to talk last term in the ZX seminar, which summarizes the result of completeness results that we have for ZX and what is the landscape of things. So I won't try to repeat that here, but if you're interested, it's available on the ZX seminar YouTube channel on on this link. So yeah, feel free to check that out. Yeah, here's the table of all the results that we have, and this work is proving completeness for ZX in the universal fragment for all of finite dimensional Hilbert spaces. And this work is going to be is going to use the ZW calculus and try to translate the completeness from that. So these are the two relevant papers corresponding to this work. So there are two common approaches that people take when proving completeness. The first is completeness via a unique normal form. So in this approach, you first show that there is a normal form, and that normal form is unique. And then you show that every diagram can be reduced to this normal form. So that implies that if you have two diagrams that are equivalent, then they can be reduced to the same unique normal form, which means you can prove that they are equal. But the approach that we will take here is the second one, where we already have a calculus that's complete, and we can translate the completeness result from that calculus to the calculus that we care about. So in this case, that will be the ZX calculus for us, and we will translate the completeness from the ZW calculus. So what is the main strategy to prove this? Well, let's say you have two calculi, C1 and C2, and C1 is complete. Then to prove that C2 is also complete, we first need to show that there's an invertible translation from C1 and C2. So, which means that you can go from C1 to C2 and C2 to C1, and when you perform a round trip, that brings you back where you started from. And apart from this translation, you need to prove that all the rules of C1, when translated to C2, can be derived using the rules of C2, which means that which means that C2 has sufficient rules to derive all of C1. And because C1 is complete, that also implies C2 is complete. So this is the strategy we'll follow for proving completeness here. And here's the summary of the talk. So first I'll introduce the finite dimensional ZX calculus. And then I'll introduce the ZW calculus, which we will translate the completeness result from. And step 3 is translating from ZX to ZW and ZW to ZX. And then in step 4, I'll show the completeness proof and end with some open questions. Okay, so here's the calculus that we're going to work with. These are the generators. Now, each of the wires in our calculus will have a label, and that label corresponds to the dimension of the wire. So when you're just working with qubits or just qudits, you don't need to label your wires because they're all the same dimensions. But when you're working with the mixed dimensional case, you need to specify by labeling each wire what the dimension of that wire is. So this is a very minimal set of generators. So first we have a phaseless Z spider, which goes from the same dimension, A of all wires. And next we have this phase part. So this is just a state. Oh, all the diagrams here go from top to bottom. So this state Z spider, so we are representing with the green box, has a label R, which is a vector in, it's a minus one dimensional complex vector. And finally, we have the generator that makes things mixed dimensional. This is the mixed dimensional Z spider, or when you just one in, one out, that's the embedding. So this goes from dimension A to dimension B. Now, apart from that, we also have the X spiders. And so as generators, we'll only take the 2 input, 1 output X spider, which goes along the same dimension A here. Then we have this state X spider, which is KJ. And this is like the jth basis state. And finally, we have identity and swap. Now, the interpretation of these generators as follows. So the Z spider, the qudit Z spider, is this one here, same as the qudit Z spider, which means for all the basis state from k equals 0 to a minus 1, it simply matches all the basis states. Now for the state, if I have a state labeled R, that is sum over all k, where you have R sub k as a coefficient. And finally, this mixed dimensional Z spider, it is like a projection. So if it's going between A and B, then it's a projection on the first common basis element. So it matches all the basis states from 0 to minimum of A or B. So for example, if you had a Z spider label 2 and 3, then it will match cat 0, cat 1. But for cat 2, it will have a 0 coefficient. Now, these are the X spiders. So 2 input, 1 output X spider is simply addition modulo your dimension. So addition modulo A. So if I input KL, it gives me K plus L mod A. And the state X spider label KJ is cat A minus J. And this is just identity. Now, using these generators, we can obtain some, there's also swap, which does what swap does. Now, there's also extra generators which we can derive using these. So firstly, we have the qudit Z spider. And this qudit Z spider is same as connecting a phaseless Z spider with the phase state. And that acts like the qudit Z spider where it matches all the dimensions and have coefficients given by this vector R. But more interestingly, we can define the mixed dimensional Z spider. And here, here the Z spider can have all of the legs can be of different dimensions. So here we are labeling A1 to AN and AN plus 1 to AN plus M. And the way it's defined is that you need to pick out which of these wires is the smallest dimension. And let's call that A. And then you just use a qudit Z spider, which is of the smallest dimension A. And then you have a projection or embedding on all of its legs of the appropriate dimensions. And the interpretation of this is that it is matching all the basis state and has the same coefficients given by RJ, except now it will only go up to A minus 1, which is the smallest of these dimensions. So it behaves same as a qudit Z spider, but it projects out up to the smallest dimension. Okay, now we can also define the X spider using this, and it's defined inductively. So first we can have this n plus 1 to 1 state, and the way it's defined is you simply compose this 2 in 1 out X spider n times. And to define it to be, for the multi-input, multi-output case, you simply connect the uh, connect it like this. And we can also have these Pauli's X spiders by connecting it with the KJ state. And the interpretation of this is we sum over all of the basis state such that the sum of the inputs, so J1 to Jm, and sum of the outputs, K1 to Km, is same as the label I modulo A. So I plus J1 to Jm is equal to K1 to Kn modulo A. Okay, now two new generators are these well, not new, but so multiplier is a qudit generator, which is a Z spider connected to X spider with M legs. And it's called a multiplier because it multiplies the basis states modulo A. And then we also have this dimensional splitter, which is like splitting the wire without changing any information. So if you have one wire of dimension A, other wire of dimension B, you can combine them into a wire of dimension AB, and that's an isomorphism. And we can define that using the mixed dimensional ZX, where we embed first on A leg and B leg to AB, and then we do like this modular addition to get IB plus J. Okay, so these are all the generators. Now I'll talk about the rules, but if there's any questions about definitions of any of these, let me know. Okay, so let's talk about the rules. So the first rule is the fusion rule. So if I have a spider label R and S, I can fuse them, and this will result in a new spider where where the vectors are multiplied element-wise. Now, because these vectors may be of different length, we always cut off to the vector which is smaller. Next, we have the color change rule. So Z and X can be color changed to each other using the Hadamard. There's bialgebra. And so these are some different ways of writing the dualizer. The dualizer is the thing that lets you bend legs of the X spider. And it's saying that the dualizer is same as 2 Hadamards or -1 multiplier. And this is just the identity ZX spiders. So 1 in, 1 out, Z and X spiders labeled with just one is identity. Okay, sudden group of rules. Here we have the copy rule. So now here notice that this copy rule goes between 3 different wires. So we have a KJ on wire dimension A, and it's being copied through Z spider in wire dimension B and C. And what this rule says is that it gets copied, but you get this extra scalar here. And what the scalar is saying is that when J is less than minimum of A, B, or C, so when J is less than A, J is less than B, and J is less than C, then I just get the states to I just get a copy of 2 states like this. But when it's bigger than any of these, then I get a scalar 0. So in other words, copy works when you're not exceeding the dimension. Otherwise, you get a 0 diagram. This is just an empty scalar. And here's a Pauli push rule. So this is just a qudit rule. So we have basically copied it here. This is how dualizer changes the direction of the vector of the Z spider. And this rule is also this rule is a qudit version, sorry, a mixed dimensional version of the Hopf rule. And like here, this B means there is B number of wires between the Z and the X spider. And what this says is that when you have B number of wires and you're projecting from A to B, then that's same as having no connection between them. So if you know the Hopf rule in qubits, where you have two wires between Z and X, you can remove them. This is analogous to that. And this is a rule that comes very naturally when you think about the ZW calculus. And what this means is that here, this part with dimensional splitter and B is doing the modulo A operation. And what this means is that if I sum A and sum two wires, modulo AB, and then I take modulo A after that, that's same as just adding the modulo A in the first place. This will appear later when I talk about translation between ZX and ZW.
Razin, I have a question.
Yes.
So if you go to the previous slides, you have the color change, and that brings you a scalar. And we notice that in the cubic case, it's not like this. We don't have a scalar. And why in the mixed dimensional case, you would have this x, yeah.
So this scalar is just so this scalar um in the qubit case, you can also redefine your Z and X spiders to get the scalar, and the reason for the scalar is you will notice that in our bialgebra rule there is no scalar. So if you remember in qubit ZX calculus, if you have bialgebra or copy rules, there's always a scalar. And then there is this well-tempered version of ZX calculus where you can introduce the scalars in the definition of X spiders such that you get a scalar in color change, but you don't get any scalars in bialgebra or copy rules. So it's a trade-off that you can make. And like doing that, um, I, I feel like has nice benefits that when you're applying bialgebra and copy and like a lot of common rules, you don't really see that scalar. Whereas if you're just saying X spider is defined like this, then even that scalar vanishes because into the definition.
Oh, so I can think of the HZ rule as a way to define the X spiders.
Yeah, yes, but then you need to change the if you change the generators here to include the Hadamard box, then you can think of HZ rule as the definition of X spider.
Got it. And another question is, in the slide, you have this like a split where the dimension on the input is A and the dimension on the two outputs are B and C. Um,
Mhm.
and but yeah, for example, like here. But I also noticed that in the previous slides you have split, but the dimensions on the input and output are the same. So does it mean like whenever you give a split, it's unless you clearly specify the dimension, you cannot just say the dimension on all wires are the same or different. It's up to how you specify
Do
them.
you mean like, for example, here?
Yeah,
So okay. Uh, so yeah, here for any Z spider, you always have to label the legs. But here we don't really need to do that because if you consider this bialgebra rule, X spider is always of the same dimension. So all the legs of X are always going to be A, which kind of fixes what this wire can be. So that's why we can be a little bit sloppy and not write the dimension.
mm. And the dimension in S1 could also could be different for different wires.
Yeah, so here you can see the labels that are like it's their label here with dimensions. Yeah.
Okay, thanks.
Wait, I didn't. Okay, so here's the okay. So here's the third set of rules that I don't think I covered these. Um, this is the dimension change for X spider, and what this is doing is that if I have A and B and I I embed them into dimension of A plus B or larger, then whatever I add modulo A plus B is always going to be the number itself. So like the modulo operation is not going to do anything. And what this is saying is that I can also increase the dimension and it won't do anything because the maximum ket that you can get from wire here and wire here is A plus B minus 1 or A plus B minus 2, sorry. That's why uh, if you have higher dimension of X and you're taking, which is doing the modulo operation, that's not going to do anything. So you can freely increase the dimension here. Now this is the phase addition rule, where if you have two Z spider P and Q and connected with the X spider, you can compute a Z spider labeled R. And what this is doing is simply a discrete convolution over P and Q. Now this is the normal form of Z spider. And yeah, this is a bit of an ugly rule because we need to explicitly say that the Z spider can be written in a normal form where each of the entry of the Z spider is a spider in this diagram. But yeah, this is necessary to prove to translate to ZW. And this is the phase copy rule, which says that if I have P, if I have Q, it can get copied to P and P when there are some special conditions on what P and Q can be. And in particular, what this means is that if I have Pi times Pj is same as Q of Q sub I plus j mod A, then this rule works. But in general, this is a simpler way of like copying through X spiders. And then there is this really big rule, which is the WW rule. And yeah, it's I don't think I have very good intuition to explain here, but all I can say is that this is a translation of the ZW rule, where you have a bialgebra between W and W. Yeah, we tried to come up with a nicer reduction of this, but it seems very difficult. Okay, so that's the summary of that's the ZX calculus for finite dimensions with generators, interpretations, and rules. Now I'll talk about the ZW calculus, which was so it's based on this paper by Wisma and Wilmar from last year. So inside W calculus, you have these generators where here's the Z spider, which goes between yeah, here between n and m wires and like has the same dimension along all of the legs. So this is the main difference between our Z spider and their Z spider, which is that our Z spider can go between wires of different dimensions, whereas for them the dimensions are fixed. But on the other hand, they have a W node, the W monoid, which can go between arbitrary number of arbitrary dimensions. So here you can see it's going from A to B1 to Bn. So these are the main generators, Z and W. Apart from that, you also have these kets. So this K just means ket K. Now using these generators, which we can interpret them first of all like this. So the Z spider is matching all of the basis states as shown here. But now notice that this Z spider only has one label, which is R. So it's just labeled by one complex number. And every coefficient becomes R to the power K. So for us, we allow the Z spider to be labeled by a vector, and the vector gives you freedom to choose coefficient for every term in the sum. whereas here it has to be r to the power k. And then there's this square root of k factorial, this normalization sort of term, which you need to have nicer rules. And the W node is interpreted like this. So if I input k1 to kn, that becomes the sum k1 plus kn. So this W node adds all of the basis states into the single wire. And whenever the dimension is smaller, it will just cut off that sum. So the sum needs to be less than the output dimension. And there are these combinatorial factors that are needed to have like bialgebra. And here's the interpretation of the rest. It's all pretty straightforward. And these are the rules of ZW calculus. And I think there are several. So this is the rule from the first version of their paper, which we use to translate in our paper. But in the second version that they updated on archive, there's only 12 rules, so it's simpler. But since we translated from the original version, we are going to use these set of rules. And they proved that these generators and rules are complete for finite dimensional Hilbert spaces. Okay. So now we can begin by translating between the two calculi. So first I'll show how you can go from Zx to Zw. So for this, we'll say we have a functor which goes from Zx to Zw, which we'll label by brackets xw. And here's how it's defined. So we have to define how this functor works on each of our generator. So when we have state labeled by vector r, we can translate it to Zw, and it translates to this normal form. So this is the normal form they have in their calculus, and we can directly translate it to that. For this mixed dimensional Z spider, where we have label A and label B, that becomes one input, one output W spider with label A minus 1, B minus 1, when A is greater than B, or it's flipped when A is less than B. And that's because the W node makes the difference, it differentiates between the input and output. Now for the Z spider, the plain Z spider, we can translate it to the Z spider of the ZW calculus. But notice that we had these extra factorial terms that were there in the Z spider of ZW calculus. So to correct for that, we need to have this extra term connected to the Z spider there. For the kets, kj, we can simply translate it to their ket j. And we need to have these extra factorial corrections. So you'll see these factorial corrections all everywhere. And now for translating the X spider, so that's the tricky part. But note that if I just ignore all the coefficients of the W and just look at what it does on the basis states, it's simply doing addition. So if I input K and L, I will get K plus L. And on the other hand, the X spider is also doing addition, but it's doing addition modulo your dimension, so addition modulo A. So the trick here is that we want to, when we translate from Zx to Zw, we want to somehow take into account this modulo operation. So what we will do is we will first of all do the addition from dimension A and A to dimension 2A. So it will preserve all the information. And then we will construct this modulo A box in ZW that will send whatever number we have to that number modulo A. So we'll do this in 2 steps. So here's how it works. So this is the X spider. It gets mapped to the W spider where we have A going into 2A. And these are some factorial correction terms. And then we have this modulo A box that will change from 2A to A. This should be A. And it will do the modulo operation. And the way this works is you can use this gadget in ZX to perform modulo operation, where we have the dimensional splitter, and you post select on one of the legs being anything. So on just being Z. And when you translate this to ZW, it looks like this. And this box will perform the modulo. So now we'll add two numbers, K, L, to K plus L, and then this box will do K plus L modulo A. And that will behave in the same way as the X. And we can prove that all these things that we translated to are sound, or in other words, the translation preserves the semantics. So when you translate from ZX to ZW, you still get the same linear map. All right, the next step, which is the easier step, is to go from ZW to ZX. And for that, we also have a different functor, which will be labeled by these brackets, WX. And here's how it's defined. So for Z spider, labeled by R, we can simply have another Z spider in ZX, labeled by R to the power n, and you have a square root of n factorial term. For the W spider, we know that W spider performs the addition, and we want to do the addition with X now, but since we don't want X to do the modulo part, we will simply increase the dimension in the middle. So we add all the dimension up for the output wires, and we say that this X spider is of that dimension. So now when we perform the addition, it will not, everything is less than B plus 1, so the modulo operation will not do anything. And then we can project back down into the respective dimensions using the Z spider. So that's Z and X, Z and W, and the rest is just some simple generators. And this translation is also sound, so it preserves the semantics. Okay, now for the proof of completeness, the first thing we need to show is that the translation is invertible, which means if I have a diagram in ZX, which is called D, and if I translate from ZX to ZW, and then I translate from ZW to ZX, this round trip should be same as the original diagram D. And to prove this, well, there's a lot of lemmas in the paper that show how to prove this, but I'll give two examples. So here's the Z spider, and here's how we can prove this. So first, the Z spider we convert to ZW, which gets mapped to this, and then we map this back to ZX, which gets mapped to this, and then we can apply some fusion to get back to the original diagram. Now for the X spider, we can take this X spider, map to ZW diagram over here, and this ZW diagram can get mapped to another ZX diagram like this. And then we perform some fusions and some non-trivial lemmas are going between these. And in the end, we can show that we get back the X spider. So yeah, this allows us to show that translation between ZX and ZW is this round trip preserves the original diagram. Now, step 2 for proving completeness is to show that all the rules of ZW are derivable using the rules of ZX, which means if you have two diagrams D1 equals D2 in Z, which you can prove with ZW, then translating them to ZX, you can still prove their equality just using the rules of ZX. And to prove that, all we need to show that all the rules of ZW can derive using rules of ZX. So we need to show all of these are derivable, which is done in the paper in all of these lemmas. Yeah, I'll give two examples of how these calculations look like. So here's the fusion. So I want to prove that in ZW, if I have two spiders connected like this, they fuse to this. And this is simply a consequence of spider fusion in ZX. So I translate, I apply the spider fusion, and the diagram I get is the fused Z spider in ZW. A little bit non-trivial is the ZW bialgebra proof. So this is the bialgebra between Z and W. So you can apply, you can see that this is the first diagram, which gets mapped to this and this is the other side of the equality. And proving that means first you need to translate, and then you apply some spider fusion. And you can see that the main step that makes the ZW bialgebra happen is the bialgebra between ZX. So now we apply the bialgebra between ZX, apply some more spider and fusions to get the ZW bialgebra form. So in summary, because we have a translation that's invertible, and we have that all rules of ZW are derivable by ZX, that gives us the completeness of ZX, which says that finite dimensional ZX is complete, or in other words, if you have two diagrams, D1 and D2, if they have the same linear map, then you can prove that they are equal using ZX. And here's the formal proof of how this works, but it's basically like those two steps. Now, a corollary of this is that ZX calculus is monoidally equivalent to the category of finite dimensional Hilbert spaces. Or in other words, everything that you can do in finite dimensional Hilbert spaces can be done equivalently in ZX. So yeah, this is saying everything you can do with linear algebra in finite dimensions can be done with ZX. Okay, so and any questions about this completeness proof so far?
I have a question.
Yeah.
So you presented the complete set of rewrite rules as like, oh, you started with the ZX rules, and to show that these rules are complete, we need to show they could be used to imply all the relations in ZW calculus, right?
Yeah.
Uh, but when you're finding the complete set of relations for the finite dimensional Hilbert spaces, based on what did you conjecture, oh, we believe these are complete and these are sufficient for us to do all the rewrites?
So if you go backwards, so you have you have the rules of ZW calculus. So you have all of these rules. If I just blindly translate all of the left hand side and right hand side of the rules here, that will give me a set of rules in ZX. And by by uh, by definition, they are going to be complete, or like they will be sufficient to derive rules of ZW. So this tells you what the rules need to be. But then once you've translated ZW to ZX, you can start simplifying. So I can see that, okay, instead of having a spider fusion rule that is a translation of this rule, I can simply have a spider fusion rule in ZX. Or instead of having a bialgebra, which is coming from translating uh, this bialgebra, I can simply reduce it to the bialgebra of ZX. So you start backwards. You start by um, starting from these rules and um, trying to simplify the rules you get in ZX. And sometimes you fail to do that, and that's why this bialgebra rule for between the W results in a very complicated rule that we couldn't find a way to simplify.
Right. So now, can you use the insights when you're working with the ZX calculus to imply maybe there are some rules in the ZW calculus that are not necessary, so you can further remove redundant relations from this table?
Um, I, I mean, in theory, yes, that's possible. That you see that sometimes two rules are uh, yeah, two
Dependent?
rules can be derived from something else. But
Yeah.
yeah, I think in practice that's more difficult because You already have something that you're trying to get to. And so in this ZW paper, they actually reduced this rule set that's given here in the second version of the paper to only have 12 rules. And they proved that this is a minimal set of rules. So that means that no other rules can be derived using, sorry, no rule is derived using any of the other rules. So if you remove any single rule from the table, the calculus becomes incomplete. So since they already proved that, so that table would not be, so you wouldn't be able to remove something from that. But yeah, I don't think so. In theory, what you're saying is possible, but I don't think we had any good insights to remove rules from here.
Okay, thank you.
Okay, so just to end, we have a few open questions. First is, what is the mixed dimensional X spider? And so we were trying to come up with mixed dimensional version of X spider, and um, everything that we could think of had um, well, some desirable properties, but some not very nice properties. And it was not very intuitive. So it would be nice to come up with a natural feeling definition of mixed dimensional X spider that interacts nicely with the mixed dimensional Z spider. Next is the minimality question. So the ZW calculus has 12 rules in their minimal rule set, whereas the ZX calculus that I presented here has 16 rules. So this is far from being minimal. And we actually don't know if we would even need 12. We might even be able to reduce it to something smaller than 12. But yeah, this is an open question that would be very interesting to explore. And lastly, can we prove completeness using only phases? So in the original qubit ZX calculus, when you label a Z spider, it's not it's not a complex coefficient, but it's a phase. So it's e to the I alpha. So if you only restrict to Z spiders with these phase elements, can you still prove completeness? Because then it would be more analogous to what the original qubit ZX calculus was. Yeah, okay. I think that's all I had to say. Thanks a lot.
Thank you. Let's give Razin thumbs up or whatever to express our appreciation for this interesting talk. Does anyone have questions for Razin? So, may I follow up on my previous question?
Yeah, sure.
So you started with the ZW calculus rewrite rules and then you translate it into the ZX rules. But what if you started with the minimum ZW rules and you translate those rules to the ZX rules? Wouldn't that bring you closer to the minimal set of rewrite rules?
Yeah, for sure, because there were some rules that we had to add to prove some of the rules here, which have now been removed. So yeah, I think it will definitely reduce the number of rules in the ZX translation. But yeah, I think the only reason we have not done that yet is because uh, when we did the translation, they didn't have a minimal rule set, so we haven't gone and updated it.
Mm.
But I don't know if we actually want to.
Leah, please.
Hello. Thanks, Razin, for the talk. I think I must have already asked this, but if you wanted, say your goal was to get like ZX plus like stabilizer plus non-stabilizer rule set for like say some fixed odd prime dimension, um, does taking the restriction of your mixed dimensional rules to like a certain fixed dimension, does that give you completeness for that specific dimension?
Sorry, I didn't follow.
Well, first of all, does taking the restriction of this mixed dimensional ZX rule set, does that give you the completeness for like like one specific dimension, the specific dimension you fixed all of the rules to?
So you don't allow for spider rules to have different dimensions. So
Yeah,
some of the rules, like for example here, XM just goes away.
yeah, that's right. Would you still have completeness for a fixed dimension if you don't allow any, like say if you, hmm,
That's an interesting question. Um, I'm not sure. So the only rules that have different wires of different dimensions are spider fusion, this copy. So spider fusion copy will work in the same dimension. The Hopf law, yeah. So for example, this would definitely need to be updated to. You would need to add a equivalent. You need to add something equivalent here for the qudit case.
uh, I see.
So yeah, I guess that would already break it, I believe.
Yeah, I guess we could look at the proof again and see which steps require going into mixed dimensions and which ones of those you can reproduce with uh just fixed dimensional rules. Okay, that's helpful. Thank you.
Yeah, I feel like it's very unlikely.
Okay. That sounds fun. Thank you.
May I ask another question?
Yeah, go for it.
So here you're talking about the rewrite rules for any linear maps. What if you restrict it to special types of linear maps like unitary isometries? What would be changed in like do you need to do any adjustment for rewrite rules, or it's not possible like just by
So I guess what you mean is that we also want the like the all the rules to be unitary.
yeah, or like
Mm.
we kind of have more restrictions on the linear maps. So, for example, for maybe K0, it will not exist because it's not really talking about the rewrites between unitaries.
Yeah, but I'm not sure. Like, for example, even spider fusion will not exist because both of these diagrams are not unitary.
Mhm.
So one thing is true that because these rules are complete for any linear maps, they are also complete for unitaries and isometries. But if you also want to have rules of your calculus to be between unitaries, so both sides of your rules have to be unitaries, then I don't think there is an easy way because like even the spider fusion rule will not exist.
Right.
So maybe there's like a yeah, limited form of this rule that could exist, but I'm not sure.
So, there's a like a cliche question for everyone doing group presentation like this kind of rewrite rules is what would you be like how would you apply these rewrite rules? Like what would be a potential use case of them?
Yeah, I think the like in my opinion, the main thing is that a lot of physics does not just work with qubits or qudits. Like it has interactions going from like any Hilbert space to any other Hilbert space. So like this already opens up a lot of like a lot of areas you can apply to, especially in physics, for example, where um, like for example, you're talking about interacting like spin systems where you want to describe how two spins couple with each other. So all of these sort of very basic problems in physics are now something you can tackle with ZX. So I think that's like a main one. Uh, well, I mean, one obvious thing you can do is mixed dimensional quantum computing, which is a bit niche, but there are reasons why that's interesting, and this is a calculus where you can start defining rewrite rules and algorithms for simplifying mixed dimensional quantum circuits. Yeah, I think those are like two main applications that I can see from here.
So suppose you have a mixed dimensional quantum process and you map this to diagrams composed of the spiders here, and you perform a sequence of rewrite rules to simplify the diagram. Is it easy to map this diagram back to like the model that you're using to do actual quantum computation? Like, for example, the spin system that you started with?
I think yeah, and this is like equivalent to the circuit extraction question, right?
Mhm.
Yeah, I mean, I don't know. It's something like we need to study, but I don't expect this to be very easy in general because there is like unless we are working with some like restricted systems where there's uh nice symmetry that we can exploit, like this shouldn't be easy.
Thank you. Does anyone have questions for Razin? Razin, do you have questions for the audience since we have a little bit more time?
Um, I don't know, maybe I would ask this. So like here we see this like the stabilizer fragment, and I was wondering if anyone knows like how you can generate the stabilizer fragment for the mixed dimensional case. So by definition, these are the maps that commute with Pauli's, right? So anything that sends Pauli's to Pauli's is a um, would be here. But does anyone know what how we can generate this fragment, or like what would be the like in the qubit case, all we need is like C naught, phase gate, and the Hadamard gate, and that would generate the stabilizer fragment for qubits. But does anyone know something similar for the mixed dimensional case?
Well, I can recap what I know so far, which is so there's good papers recently on qudit computation where they define the stabilizer fragment, and I think the kind of issue that is that they can define the stabilizer fragment for non-prime dimensions, but it's not that it has a clear like it they don't know. So the authors of the paper I'm referring to by Jennifer Pakin and uh I can link the paper once I find it. Um, so they can define by definition the stabilizer fragment for Qubit for non-prime dimensions as the like based off the Clifford, just the usual definition of uh commuting like of the things that polys commute with um to change to a different poly. Um, and the problem is that they didn't know what is a generating set for that. So like it's only for the qubit case, prime dimensions that you know that C naught, S, and H gate generate all the unitaries for the stabilizer fragment, but they don't know what is a generating set for the non-prime dimensions. So it's not that you can't define the fragment or know what its properties are, but that you don't have like a gate set you don't know of a gate set which generates it.
But I
That's
wonder if like
my knowledge.
if you're working with ZX, maybe there's like a little bit more freedom. Like we don't need the generating set to be a to be circuit elements. Maybe there's
Yeah,
it
but
could
I
be
guess
easier.
you still need to have generators rather that of the fragment rather than just yeah rather than just like you still need generators of the fragment rather than just properties that they hold. As well, the matrix elements doesn't tell you enough. Like I think, for example, in qubits, the rings, like the matrix elements that the Cliffords are in, is also the same matrix elements that, like, say, Toffoli plus Hadamard, the phase-free, like just like Toffoli plus Hadamard fragment is in. So just the matrix elements doesn't work either. But maybe that could be a place to start because they're clearly it's adding like the Toffoli that goes past the Cliffords. Well, actually, it doesn't have the Cliffords either. No, actually, sorry. For the Qtrit case, for Qpit case, it does. Yeah. But that's also only for prime dimensions. So I'm kind of rambling. Yeah, I'll think about it more. I'll link the paper now. Let me find it.
So by the way, Razin, in your rewrite rules, you have those like dimension A and modulo A. Are those like any dimension or they must be prime?
They can be any dimensions.
Uh,
I don't think there is, there is no restrictions on the dimensions here for the generations. They can be any natural number, any natural number greater than or equal to 2.
it's interesting how when you go from the circuit to the diagrammatic lens, the derivation of completeness results become so much more systematic. When we're in Qtrit, even just working with Clifford relations, it depends we have to really rely on like p equal to 3 and a lot of like other properties of the underlying numberings itself. But when you're working with ZX calculus, you have so much freedom to bend wires and use all those kind of rewrite rules, which is just amazing.
Yeah, I think that definitely makes things easier. Especially like you get a very simple normal form in if you're trying to derive completeness from normal form, you just have a normal form, which is the matrix.
Mhm.
So you don't really need to use a just like what is the normal form when you're working with qubit circuits?
It's a little bit like Gaussian elimination. So imagine
Mm.
you're working with a stabilizer tableau, and then you just because every Clifford corresponds to an automorphism. So on Pauli, so you just recursive inductively, well, it's not inductive. So yeah, it's inductive. You just inductively reduce the actions on Pauli's from the n qubit qubit to the n minus one qubit, etc. So you basically concatenate a normal form that kind of every layer deal with one qubit.
Mhm.
And and that corresponds to a Gaussian elimination on the Z Pauli basis and an X Pauli basis. Yeah.
I see.
And like for example, like you have this very nice translation between ZW calculus and ZX calculus to use a known result to infer an unknown result. But thus far, I haven't seen this in like circuit land. Like you always have to start with the normal form. So I'm actually I would be very um curious to see if people could use some known rewrite rules to infer the rewrite rules in a different land. That would be really cute.
Mm. Like coming up with circuit identities based on ZX rules.
Yeah. Okay, so
Paul had a reply to the stabilizer question, which was for odd prime p and positive natural number n, affine Lagrange relations over fp to the n is a subcategory of q qudit stabilizer circuit modulo scalars, but it is missing some generators when n is not 1. So I don't even know how or what the odd prime power stabilizer X rule should be.
So, can you hear me?
Yeah. Sorry, I was just reading your
Well,
message.
I was just, yeah, my internet's really bad, but I was just saying, if you wanted, with, I think Leah's question, but my internet cut out. If you want to like talk about all stabilizer ZX calculuses together,
Hmm.
even if you only restrict yourself to the ones which are not even dimensional, I don't even know what the generators would be for odd prime power qudits, because the conventional methods, like if you just generalize like the qubit stabilizer ZX calculus to fp to the n, then this doesn't actually get you n qubit stabilizer circuits. It's different. It's not, yeah.